This is the Infinite Series Help Center. We guide infinite series and help them figure out where they're going, converging or diverging. A series converges when the sum of all the terms is a finite number, and diverges when the sum of all the terms is not finite. This is the first customer. He needs help to figure out if he's going to diverge or converge. We'll refer him to our go-to guy, the nth term test. The nth term test will take the limit of his equation. Since it's not zero, he'll diverge. If you continue adding terms that are not zero, then the series must add up to infinity because the sum would keep getting bigger. Here we see another customer needs help, but sadly the nth term test cannot help since the nth term test only proves divergence. Let's take a look at another series. Because he's an alternating series, we'll refer him to the alternating series test. If the limit of the absolute value of the series is zero, it converges. If it's not zero, it diverges. The limit is zero, so this series converges. When a series converges according to the alternating series test, the size of the terms gets smaller and smaller, and the series gets close to one number. When the limit is not zero, that means the size of the terms never decrease and the sum keeps getting bigger, so it diverges. Let's take a look at our third customer. We know he's a geometric series because there's a constant ratio r between the consecutive terms, so we'll use our geometric series guy. For geometric series, if the absolute value of r is bigger than 1, it will diverge. If smaller than 1, the series converges. When r is bigger than 1, the terms increase exponentially, so it diverges. When r is less than 1, the denominator grows faster than the numerator, and the terms grow closer to 0, meaning convergence. This customer's r is less than 1, so the series will converge. For a geometric series, you could find the sum of the series using this equation. Our fourth customer is a bit unique. We can use telescoping series test because it is an equation minus an equation, or we can also use him if the denominator is factorable. This series wants to figure out where he will converge to. We'll use our telescoping series guide to find the sum by listing off terms till they cancel out, and find the general term and the limit of that term to see what the series approaches. For our fifth customer, we set him to the integral test. The integral test only treats customers if they are continuous and decreasing over the interval 1 to infinity. The series will converge if the improper integral value is finite and will diverge if not finite. This series has a finite improper integral value and therefore will converge.
Our sixth customer is a p-series, so we'll use our p-series theorem helper. A p-series is when n is raised to a power p. A p-series will converge when p is greater than 1 and will diverge when it's less than 1. For this example customer, the p-series will converge since its power is greater than 1. The p-series theorem is a helpful worker at our clinic as he is often used in different tests such as the direct comparison, limit comparison, and absolute/conditional tests, etc. Next, we'll refer this customer to the direct comparison test helper. The DCT helper states your series will converge if it's smaller than a convergent benchmark series. If your series is larger than a divergent benchmark series, your series must also diverge. The direct comparison test helper compares the customer series to a converging p-series that is bigger than him, and therefore the series also converges. The direct comparison test helper can sometimes lead to an inconclusive result. If your series is smaller than a diverging series or greater than a converging series, that doesn't prove anything. Our next helper, the limit comparison test, is the direct comparison test's cousin. It divides a series by another series and takes the limit, which produces r. If r is finite and not zero, both series will either converge or diverge. This customer series leads to an inconclusive result, aka when r equals 0, when comparing to 1 over n squared. This is because the limit comparison test only works when you choose a comparison series that has the same n behavior, like choosing the same highest degree or a common ratio. Let's compare the customer series to the converging p-series 1 over n to the third, since it has the same n behavior. The limit comparison test results in a finite number that is not 0, meaning the series also converges since 1 over n to the third converges. The customers keep coming. Our next customer is composed of the product/quotient of terms that have different growth rates. We'll use our ratio test helper when those types of series need help. We can find R with this formula. If R is less than 1, the series will converge. If it's greater than 1, it will diverge. If it's equal to 1, it is inconclusive. For this customer, we'll use the ratio test helper in its equation. Once we cancel out a few terms, we can take the limit of the remaining terms. The R value of this series is less than 1, meaning this series will converge. Another customer wants to know if he's going to converge or diverge. We sent him to the ratio test, but since he's only made of polynomial terms, the ratio test cannot help him. For series made of only polynomial terms, the series will always be inconclusive. Our second to last customer knows he is a converging alternating series, but he wants to know if he's going to converge conditionally or absolutely. Conditional convergence is when a series converges, but the absolute value of the series diverges. Absolute convergence is when the series and the absolute value of the series both converge. For this customer, we'll take the absolute value of his series, which results in a diverging harmonic series. Since this customer converges, but the absolute value of his series diverges, he will conditionally converge. Our last customer of the night knows he is a converging alternating series. He wants to know if he's going to converge conditionally or absolutely. Both the absolute value of the series and the series converge, so this series converges absolutely. Thanks for coming to our clinic. We hope you enjoyed learning about infinite series and the different tests used to find if infinite series converge or diverge.